Hey everyone, welcome to Chapter 9. In this lesson, we will go over steps on how to manually build a limb rig. In the following lessons, we'll learn how to automate the entire build process. Because there's a lot to cover in Python, I wanted to keep the setup relatively simple. Our limb will have IK-FK switching and stretch, but no bendy or twisty joints. FK stands for forward kinematics and IK stands for inverse kinematics. Very simply put, with forward kinematics, when you rotate one control, all the children rotate along with it. This is good for animating secondary motion and overlapping action. Think of a dangly piece of cloth, a ponytail, or arms that are not carrying any weight. You can think of inverse kinematics as a linear motion. Legs 95% of the time, arms doing push-ups, locked to an object, or making a stabbing motion. IK relies heavily on translation and FK on rotation, though they are not exclusive. You can rotate IK controls and translate FK controls, as long as they're unlocked in the rig. Let's get started. Go ahead and open up the ARM starter file in the course materials, or you can create some joints on your own to follow along with. I'll hide the right side guide so we can just focus on the left. I'll then duplicate the joint chain 3 times, one for the FK chain, IK chain, and bind chain. The bind chain is going to switch between the other two, and it's what we'll use to skin our character. Using the grep rename tool on my shelf, I'll replace the guide naming with the FK, IK, and bind names. Then, I'll also remove the joint suffix we got from duplicating. Let's open our node editor and middle mouse drag these joints in there. I'll rearrange them so they're a little bit easier to read. Then I'll press tab to create a blend colors node. We'll use this to blend the FK and IK translates on the shoulder into the bind joint. We can call this L shoulder translate BCN for blend color node. So let's connect the IK's translate into color 1, the FK's translate into color 2, then we'll take the output of this node and hook it into the bind joint's translate. Next, using the EP curve tool, I'm going to draw a control shape that we can use to drive our blending. I'll call this LARM settings control. We'll need to create a new attribute to drive this value. So let's go to Edit, Add Attribute. We can call it FKIK, give it a min of 0 and a max of 1, and I'll leave the default state at 1 or in IK mode. Using 8B on the shelf, I'm just going to move this settings control and position it slightly above the hand. Then, because we won't be transforming this control, I'm going to lock and hide all the transform values, leaving only the FKIK attribute exposed. Now that we have this attribute, let's connect it to our blender value on the blend colors node. Now, if I move one of these chains off to the side, we can see this attribute controls the bind joint's position between the two chains. But right now, this is only the translation on one joint. We want it on all joints, but we also want it for scale and rotation. So let's now manually create about 10 more nodes, properly rename them, and then make 30 connections. We could do that, or we could write a little script to help us out. I'll choose the latter. I deleted the blend color node we just created because it will be recreated in the script we're about to write. Let's open up our script editor and make 3 variables for our joint chains. Then we can populate our variable with the joints by using the ls command. Next, let's make our for loop. We can zip these lists by saying for FK, IK, bind, in zip, FK chain, IK chain, bind chain. As we loop through the joints, we also want to loop through our transform attributes. So we can say for adder and translate, rotate, scale. Then inside this loop, using the create node command, we can create our blend color node. We'll name it using the bind joint, but replace the bind joint suffix with underscore BCN. Now we can start scripting our connections using the connect adder command. We'll connect the IK plus dot plus adder into color 1 on our blend color node, the FK attribute into color 2, the setting controls FK IK attribute into the blender attribute, and last we'll connect the output into our bind joint. When I run this, I get an error. Unfortunately, that's not uncommon. The good thing is, our script editor tries to tell you where the error is. Make sure you have show stack trace on in your history. This will give you a more descriptive error message. It says, invalid syntax line 9. So I know the command before this line is the one that's actually causing the error. It looks like I forgot to add the comma after passing in the node type. I'll correct that and try again. Now it looks like it has built with no errors. Let's go into perspective and pose our FK controls. Then using our settings control, our bind chain should blend between the other two. In the next part of this lesson, we'll add in some controls and have them drive our FK and IK chains. Thanks for watching, and I'll see you in part 2. Hey there, welcome back. In this lesson, we will create some controls to drive our joints. This includes building an IK handle for the IK joint chain. Let's go ahead and start by building the FK controls. First, let's make a circle. In the construction history, I'll modify the axis this control is created on to match the primary axis of our joint, X. Scale it up a bit, then duplicate twice to make our other controls. I'll arrange the hierarchy, then start using the align LRA script to snap these controls into place. Let's then give these controls some descriptive naming that matches our joint chain naming convention. Now I want to set up some connections from the control to the joint. Let's open our node editor. We'll make the connections in here. I'll load in the joints and controls with middle mouse drag, and then arrange them to make connecting them a bit easier. For this setup, I will use direct connection for the rotation and point constraints for the translation. To prevent the graph from rearranging like it just did when I created the point constraint, I will pin down all the nodes by pressing P with nothing selected in the node editor. Now when I create something, my pinned nodes don't move. On the wrist, I happen to notice that I connected my joint into the control. You want to make sure that the control is driving the joint and not the other way around. Let's now create the IK controls we want to use. We can make a square shape out of the NURBS circle by setting the degree to linear and sections to 4 in the construction history. Then rotate it 45 degrees. I'll scale it out, then duplicate it a few times for the other controls. For the first two, I'll use A to B, but with the right-click menu to only point them into position. We want the orientation to match the world space. I'll then scale these up so that they're a little bit bigger than the last one. And for this one, I'll parent it to the second and use align LRAs to snap it to the wrist. Now let's give these some naming. We'll name the top one L shoulder IK control. The next one will be L arm IK control. And the last one will be L arm local IK control. Let's make sure the transforms on all these are frozen. I'll unparent the local control when doing this, freeze the arm IK control, reparent the local control, and then freeze its transformations. For this lesson, I'm using the 2020 settings with the Align LRAs tool. When we script the rig, I'll add a few extra lines to work with other versions. The setup for both is still very similar. Again, using the EP curve tool in the orthographic views, I'll draw some points that we can use for our pull vector control. I'll then snap it into position and freeze transformations. We can call this L-arm PV control. This is getting visually difficult to tell what's going on. I'm going to unlock the drawing overrides on these control curves and assign a color value to them. Then I'll also turn off wireframe on shaded. Let's now create our IK handle. I'll isolate the IK chain by selecting the root joint and pressing Shift plus I. Then go to Skeleton, create IK handle. In the Tools headings, make sure the solver is set to Rotate Plane and Sticky is checked on. Then select your Start joint and End joint. Now I have inverse kinematics set up on this chain. To create a pull vector constraint, select the PV control, then the IK handle. Then go to Constrain, Pull Vector. If the pull vector target is properly aligned, you will not see your chain move at all when creating this constraint. If I were to move the target down here and create the constraint, you would see it snap, and that's not good. When you rotate your elbow inwards, it should be perfectly aligned with the shoulder bone. If this is the case, to position the pull vector control, you can use this icon on the shelf to create a locator at your selected object. Then, with your move settings set to object, you can translate along the arm plane to position your pull vector. I'll recreate the pull vector constraint because I hit undo a few times earlier. Then I will constrain the IK handle to my local IK control. Let's also name this L-arm IKH. Now when I move any of these controls, the IK setup should behave the way we would expect it to. Let's make sure our bind chain still blends between the other two chains. And it looks like it does, so that's great. In the next part of this lesson, we'll take a look at how we can add stretch to our FK and IK chains. Hey, welcome back. In this lesson, we'll take a look at how we can add stretching on our limb. For the IK, we want our limb to stretch as soon as the distance from our shoulder to wrist is equal to the total length of the shoulder and elbow bones. We also want to be able to offset the stretch on either bone. On top of that, we'll want to be able to disable stretch. For the FK, we'll just want an attribute to increase the length of the bone related to the control we have selected. We'll need to know the lengths of our upper and lower arm. So let's go up to Create, Measure Tools, Distance Tool. I'll just plot 2 points on the grid, and I'll do that twice. Then, I'll hold the V key to snap the points to the joints. I'll then duplicate the first and last locators and rename them L-arm start locator and L-arm end locator. We'll then use these to measure our total arm length. Let's go ahead and open up the node editor and add these 2 locators. We can remove their shape and anything else that we don't need. Next, create a distance between node. Then we'll take each locator's world matrix and connect it into the in matrix 1 and 2 of the distance node. Order here does not actually matter. Let's also create a condition node. With it, we can tell our joints when we want them to stretch. I'll name the distance node L-arm DST and the condition L-arm stretch CND. We also need a multiply divide node. This can be the L-arm stretch MDN. We'll use it to divide our start to end distance by the sum of our 2 bone lengths. So connect the distance into input 1x, and let's set the operation to divide. Then, to get the total arm length, let's just open up our handy dandy calculator and add the 2 distance dimensions sitting in our viewport together. And that will be our input 2. We'll connect the distance into the first term of our condition, and the output x of our multiply divide into the color if true r. We'll also paste in the total length value we just calculated into the second term and set the operation to greater or equal. This basically says, if the first term is greater than the second, let's use the stretch value. Otherwise, we'll leave stretch at 1. We can go ahead and delete the measure tools in our outliner as we no longer need them. Then let's add some attributes that we'll use to control our stretch. We'll add these on the L-arm IK control. First, let's add a float value called stretch and give it a min of 0 and a max of 1. We'll also set the default value to 1. This will be used to turn on and off our stretch. Next, let's add an attribute called UpArm. We'll use this to add or subtract length from our upper arm. We can leave the min and max open and set the default to 1. We can do the same thing for the lower arm. Now let's hook up these attributes into our little network here. We'll start by creating a blend2 adder node. This will act as our on-off switch for the stretch. For some reason, Maya didn't want me to pull up the attribute list and choose where to connect the output of my condition. So let's just name this L-arm stretch BTA, and we'll make some connections and set some attributes through the command line instead. Let's set the attribute blender's first input to a value of 1 using the setAdder command. Then, while in the command line, press the up arrow key to go to the last command you executed from here. Let's modify it to say connectAdder. We'll change it to input 1, and we want to then paste in the name of our stretch condition node, dot the attribute name, outColorR. Now we can load in our arm IK control and connect the stretch attribute into the attribute's blender attribute. Let's create 2 plus-minus average nodes to add or subtract length from our upper and lower arms. We can leave the operation as sum. I'll go ahead and name these L-uparm PMA and L-lowarm PMA. Then we can connect the low and up arm attributes to their respective input 1D0 attribute on the plus-minus average nodes. And I'll just do a little bit of rearranging here. Now connect the output from the BTA into the input 1D1 attribute on both PMA nodes. Just like with our BTA, to set the attribute on an input we cannot see, we'll go to the command line and use cmds.setAdder on the PMA's input 1D2 attribute, and we'll give it a value of -1. Then we'll do this one more time for the other bone. Let's add our IK chain to the graph so we can make some connections. We'll want to connect the output of the low arm PMA into the elbow joint scale X, and the up arm PMA's output into the shoulder joint scale X. I forgot to set my low arm default value to 1, but that's okay. I can go ahead and set that to 1 now. By default, our scale x value on these joints should be at a value of 1. Before we can test this, let's first point constrain our start locator to the shoulder IK control and the end locator to the local IK control. Now, when we move our arm, it stretches. We can disable the stretch through the stretch attribute on this control. And we can change the length of the upper and lower arm individually through their attributes as well. That's all for the IK. Let's give stretch to the FK now. We can start by adding a stretch attribute on both the shoulder and elbow controls. We'll have the min value at 0.001 and the default at 1. Next, select the shoulder joint, then click the locator tool on the shelf. Do the same thing for the elbow joint. You should now have two locators that match the position of each joint. Let's call this the offset locator by replacing the joint name with off. Then parent these to their respective joint. Using A to B, move the elbow locator to the wrist and the shoulder locator to the elbow. Then add these locators and the controls over into the node editor. Let's create a molt double linear for each bone. We'll call them L shoulder FK stretch MDL and L elbow FK stretch MDL. Copy the translate X value over from their offset locator and paste it into the input 1 on the MDL. Next, we'll take the stretch value for each control and plug that into the input 2 on the MDL. Then, we want to take the output of that and connect it into the offset locator's translate X. Let's drag the bones into the graph and connect our control's stretch attribute into the bone scale X. I want to mention again that for this setup I'm using Maya 2020 attributes. However, when we script the build, I will cover what to do for 2019 and below. But for now, we want to take the matrix value on the shoulder's offset locator and connect it into the offset parent matrix on the elbow control. Subsequently, we'll connect the elbow locator's matrix into the wrist FK control's offset parent matrix. Now when we activate the stretch value on the FK controls, the bones stretch as expected, and the child FK controls follow properly. The offset locators appear to be getting double transformations, but that's actually okay. It's a little hard to get a sense of what's going on when we're just evaluating what the joints are doing. Let's take our bind joints and smooth bind our arm. Now when we play around with the controls, we can check to make sure everything is functioning properly. The default skinning doesn't look great, but that's okay. It's enough to test the rig's mechanics. Let's go ahead and organize this rig a little bit. I'll start by creating a bunch of empty groups. We'll need an FK control group, IK control group, a skeleton group, a no X-form group, a rig group, and a master group. Let's parent the shoulder IK, arm IK, and pull vector controls into the IK control group, the FK controls into the FK control group, the bind joints into the skeleton group, the FK and IK control groups, their joint chains, the no X-form group, and the settings control can all go into the arm rig group. The arm IK, start and end locators should all go into the no X-form group, and we'll also want to turn off inherit transforms on this group as well. The skeleton group and arm rig group can go into the L-arm main group here. Now that we have our grouping, let's first select the shoulder bind joint, then the arm skeleton group, then the arm rig group, FK group, and IK group, and then use the match to pivot so we move all our groups to the first joint's pivot location. While we're cleaning things up, let's constrain our settings control to the wrist bind joint. To do this, we'll need to unlock some attributes first. Then we can select our wrist bind joint, then the settings control, and create a parent constraint. And notice I accidentally turned inherits transform off on this control. Let's just make sure our no X-form group has it turned off as well. The last thing we'll want to do is create visibility switching for our controls. When we're in IK mode, we don't want FK controls to show, and vice versa. Let's create a reverse node and connect the FK-IK attribute into the input X of that node. We'll also connect the FK-IK directly into the visibility attribute on the IK control group. Then, we'll connect the reverse node's output X into the FK control group's visibility. Now when we switch from IK to FK, we see the inactive set of controls are hidden. In the next lesson, we'll start scripting this entire setup. Thanks for watching, and I'll see you there. Hello and welcome. Are you ready to script a limb using Python? Let's do it. For these next few lessons, I've decided to demonstrate the code in PyCharm. You do not need to use PyCharm to follow along. You can use any editor, including Maya's. This is a lesson on Python, so I will not be going into the minutiae of PyCharm. However, I definitely encourage its use. I've been using PyCharm for less than 2 years, and it's been completely wonderful. Before that, I used Sublime, which is not a bad option either. I still use it from time to time. So over here in my editor, I'll start out with some basic imports. Make sure we import Maya CMDS as CMDS, but also we can reuse our helper scripts inside of this script by importing it. We do this the same way we're calling it on our shell. We'll also be executing this from inside Maya. To do that, we'll import the script in our editor here. We can do this just like our shelf as well because I've saved our script lim.py inside the same folder as our shelf utils.py. Let's start out by defining our function. We'll call it lim. Next, let's give it some default arguments. For now, these can just reflect what is currently in our scene. We'll give this the side name of L and the part name of arm. These will be useful for determining our naming convention. Next, let's pass in our guide joints as a list. We can select them in Maya and use the fifth shelf utility. This will print a Python formatted list. I'll just copy and paste that into my editor. This gray line on the right side of PyCharm represents the length of 80 characters. When developing in a team environment, it is helpful to adhere to PEP 8, which is a guideline and best practices when writing Python code. PEP 8 suggests that each line should not be greater than 80 characters. This is not something I cover in this course because I think it's more important to focus on writing functional code. You can always sharpen your formatting skills once you have a solid grasp on the language. Next, we'll add an argument for our pull vector. We can also add an option to remove guides after we've used them to build our setup. Also go a line up and add in an alias list so we can be flexible when it comes to naming each bone. This way we could pass in the naming for the leg as well. Let's add the option to have our stretch functionality. We'll also be using a dictionary of values to pass different coloring options into our script for the controls. And last, we'll give a primary axis and an up axis. Now that we have our arguments set, I'm just going to run a few checks. We want to make sure we're passing in 3 names for our joint and alias lists. We also want to make sure we're passing in something for the pull vector. Next, let's define our base name. This is going to be used all over the place. It's just the side name plus an underscore plus the part name. I'm just going to create 3 placeholder variables for the 3 chains we will be creating. Then I'll go down a line and start writing a function that we can use to build these chains. We can call this create chain. We'll need to give it our side name, the joint guide list, the alias list, and a suffix for the naming convention. These are all arguments that we're going to pass into the function. Let's create an empty list called chain. We'll be adding our joints to this list as we create them. To do that, let's run through a loop. To run through our joint and alias list simultaneously, we can say for j, a in zip joint list, alias list. We'll be parenting the subsequent joints to the previous one, so the first joint will not have a parent. We can check to see if j is the first item in the joint list. If it is, parent equals none. Otherwise, it will equal the variable joint, which won't be defined until the second time through this loop. Next, let's create a joint and define the variable at the same time. Using the joint command, the first argument is the parent. Next, we'll give it a name using .format. Inside the format, we'll give it the side name, the alias name, and the suffix name. Then using our shelf utility, a_b, we can directly pass in the joint we just created and the guide joint. As a general rule, I try not to use cmds.select inside my script if it can be avoided. I've also included an argument to freeze transforms after moving them. With append, we can add our newly created joint to the end of the chain list we defined previously. And last, let's return chain. That way, if we define a variable using this function, that variable will be our return value, the chain list. Now that we have written our create chain function, we can use it up here to build and define our 3 chains. I'll just copy the entire function and paste it 3 times. We'll need to change the suffix so we can build chains with different naming. To see it in action, I'll print these chains on a separate line when we run our code. We now have a script that actually does something, so we can test it in Maya. We imported the script as nmlim, so we can execute the lim function from within this script by saying nmlim.lim. When we execute this code, we can see that our 3 chains have been built, and our variables containing the joint names in a list have been printed as well. Before we move on to blending our chains, I want to show you how to calculate the distance between 2 points using Python. We'll use the distance in a few places in our script. We'll use it for a stretch, of course, but we'll also be using it to automate the size of our controls. And we want to build our settings control before setting up the chain blending. Up at the top, we can import Python's math module by saying import math. Then let's go down to the bottom of our script and start writing a function we'll call distance between. We'll give it 2 arguments for the nodes we want to calculate. Then, using xform, we'll get the world space position of those 2 points. To calculate the distance, we can use the distance formula. If you don't remember this, it's just a Google search away. This is for 2D space, but it works for 3D as well. We just need to add our z-axis. Our xform command will return a list with 3 points. We'll want to take the points b and subtract points a. We can do this using list comprehension while zipping together our 2 lists of points. So let's create a distance variable. Inside of a list, we'll use power to square b minus a, and we'll do this for b comma a and zip point b comma point a. This makes a new list by raising b minus a to the power of 2 for x, y, and z. To add these all together, we can use another of Python's built-in functions, sum. This will add up our list. Then, using math, the module we imported, we can say math.square-root, and then put everything inside of those parentheses. This gets us the distance. We then want to return this distance variable. Let's test this out in Maya. Using nmlim.distanceBetween, I'll add my shoulder and wrist guide names for my 2 arguments. Because we changed the script, we have to first reload nmlim. Then, when I run this, it should return the distance. We can use the measure tool to see if our math is correct. And it looks like 16.1067 is the same as what our variable returned, just rounded down. I'll just go ahead and clean some things up here. Okay, now let's go ahead and build our settings control. Let's do this in the front view and create this by drawing points using the EP curve tool. I'll then center my pivot and bring it to the origin. Then scale it down so it fits inside a 2x2 grid. All we're going to do is print out the point position of our points and use that in our script to draw the curve. Typically, studios and other rigging tools will have a library of control shapes, but to keep things simple, we're just going to build our curve like this. When I freeze transforms on this curve, the control vertex positions get baked into world space. You can see this if you look at their position in the channel box. To find the point position and print them out, we can write a little script inside Maya. We'll say for CV, then list curve1.cv, and inside of brackets we'll put a wildcard, and then we'll add the argument flatten equals true. This will loop through all the CVs individually. To print the point position, we can do an xform on the CV. We'll want to query the world space translation. You can then copy this printout into your curve command. When scripting with the curve command, the shape does not always get named properly, so we'll write our own little command to help that out. Let's call this function curveControl and pass in a point list, a name, and we'll set the default degree value to 1. Inside of this, we'll use the curve command to draw our curve using the data we pass into the function. Then, we'll use list relatives to find the shape node on this curve and rename it to match the transform name, shape. And then we'll also want to return the curve transform node. I'll go ahead and copy this over to the lim.py script. I'll do a little housekeeping while I'm in here. It's always good to write comments about what you're doing, not just for others, but yourself as well. I already have cleaned up my point list for this control, so I'm just going to paste it into our script. We'll then create a variable called settings control and use our new function to build our shape. Let's set the scale on our control to fit our character. To do this, we can approximate the radius we want by using a fraction of the arm's length. That's one reason we wrote the distance between function. So let's use it to measure from the first joint to the last joint, then divide by 5. We can then set adder on the scale by using a quarter of the radius for the x, y, and z values. Next, we'll check to see if our up-axis is positive or negative. If it's negative, we'll negate the values we're translating it by. Otherwise, we want it to remain positive. What we're doing here is offsetting the control from the wrist. We'll then freeze the transformations, parent constrain it to the wrist bind joint, and then add our FK-IK switch attribute. I forgot to add one step, so I'll go ahead and do that now. Using align LRAs, I'll snap this control to the wrist. I'm defining this in a variable because I modified the function to return the offset group if it exists, or just the control if it doesn't. Now let's go ahead and write a function for blending our chains together. I won't go over this in much detail because the script here is almost identical to the one we wrote in the first part of Chapter 9, Lesson 1. Let's go ahead and add this in our limb function just after we've built our settings control. Now, when we run this, our chains should blend together. If we go over to Maya, we can test this theory by moving one chain, then using the settings control to blend between the two. And it looks like it works, so that's great. In the next lesson, we'll script the FK and IK controls. Thanks for watching, and I'll see you there. Hey everyone, welcome back. In this lesson, we'll set up our FK controls, IK controls, and IK handle with Python. Let's dive right in. We'll start out by making an empty list that we can add our FK controls to as we create them. Let's then loop through our alias names. Using enumerate, we can assign a value to each alias using the variable I. Each time through the loop, we'll create a control using the circle command. We'll use our variable r for the radius. If the primary axis is x, our normal will be 1, 0, 0. But what if we change this to another axis? Let's quickly write a function that we can use to convert the primary axis into a vector value. I'll scroll to the bottom and create a function called defineAxis. We can pass in just a single argument for our axis. Then we'll make some conditions. We'll say, if the last character in axis is x, then we'll define the vector axis as 1, 0, 0. We want to isolate the last character in case we pass in a negative value for that axis. Next, let's make some elif conditions to define the vector axis for y and z. If none of our conditions are met, we'll want to throw an error. If there is a minus symbol in our axis, we'll want to multiply our vector values by -1. I've done this inside of a tuple for consistency, but a list would work as well. Let's return our vector axis. Then, we can scroll up to the top and define this in a variable. Let's just call it PA. Now, if we go back to our control loop, we can use the PA variable for the normal value. We'll set the degree to 3 and give it a name using our side and alias. Circle returns a list, so I want to make sure that we only get the transform. We want to parent the control to the previous one created. However, the first control cannot have one before it. So we want to say if I is not equal to 0, then parent the control. Next, we'll snap align the control to the joint using align LRAs. We'll want to redefine this as control off in case there is an offset group. Then, if this is the first time through the loop, let's make a new variable for the root of our control chain. This will be called FK top group. Let's now define our parent for the next time through this loop. We can say pair equals control. The last thing to do here is connect our joint to its control. We'll use a point constraint, then a direct connection for the rotation. We'll also want to append our control to the variable we defined before the loop. It's the list called FK controls. If we run this script in Maya, we should see that a control gets created at every FK joint. When we move the controls, the joints follow along. Let's start building our IK controls. We can start with the world space IK control. We'll use a circle with 4 sections and a degree of 1 for linear. It's very important not to type the word circle with the letter U, like I accidentally did here. Next, rotate the control 45 degrees in the primary axis and move it to the wrist joint using A to B. We'll make the local control in a very similar way, except instead of using A to B, we'll freeze our rotations after the 45 degree offset, then use align LRAs to snap it to the wrist and match its orientation. We'll then parent this to the world control. Let's now make our locator shape control for the pole vector. I happen to have these points saved, so I'll just paste them. You can record your own shape using the method described in the previous lesson if you'd like. We'll then pass in this point list to the curve control function, change the scale, then translate it to our pull vector guide using A to B. The next control is our base control. We'll create this in a similar way, but pass in the alias name for our shoulder when naming it. Snap it into place, then we'll want to constrain the first IK joint to this control. Now that we've built all our IK controls, let's create the IK handle. We'll give it our base name plus IKH. The start joint is the first in our IK chain. The end effector is the last in our chain. We want to set sticky equal to sticky. We can set the solver equal to IK RP solver, and we'll set setup for RP solver equal to true. This returns a list. We only want it to return the first item, which is the IK handle. Then we'll parent constrain the IK handle to the local control, and then pull vector constrain the handle to the PV control. I'm just going to comb through my code for the IK controls here and fix a few typos that I noticed. Let's go ahead and test our code. I'll run this and then bind our arm to the bind joints. Now we can see all our controls are built, and if I move my IK controls, the arm is moving. There is one thing about this setup that I'd like to mention. We're only scripting the limb, in this case the arm. There's no hand joint. I'll quickly demonstrate how I would add that to the IK chain. First I'll create a joint and snap it to the wrist. Then I would point constrain it to the wrist joint and orient constrain it to the local IK control. To work this into the entire system, there may be a little bit more to it, but that's the gist of it. To better visualize what this would look like, I'll add the new joint to our skin cluster and quickly adjust the skinning. I noticed my orient constraint settings were only constraining the y-axis. It's good to keep in mind when you create a constraint, your settings get saved, so always be careful when you go to create another constraint. Be sure that your settings are what you want them to be. Once I fix this, my hand functions as expected. In the next section, we'll take a look at how we can script the FK and IK stretch. Thanks for watching, and I'll see you there. Hey everyone, welcome back. In this lesson, we will script the stretch for the FK and IK systems. Let's start with the IK. We'll create a function called addIKStretch. We'll be using this inside of our limb function, so we'll need to pass in a lot of information to use here. This would work if we just append the code inside the limb function itself. However, having the stretch as its own function is a better way to organize things. If we were writing this as a class, we wouldn't have to do so much passing variables from one function to the next. Perhaps the most powerful feature of classes is their ability to share the same variable across multiple functions. Though using a Python classer would be nice, I think it's important to get comfortable working with functions, and this is a really great way to do that. In the course materials, I'll include a version of this tool I've written as a class. Instead of passing in the base name to this function, I just decided to redefine it by concatenating side and part with an underscore. In this next block of code, we're just creating a bunch of nodes. You probably remember creating them inside the node editor in one of the previous lessons. Using the create node command, we'll make our distance between node, our condition node, and the multiply divide node. We'll also create our start and end locators using the space locator command. This returns a list, so we'll only want to keep the first item, which is the transform. Next, we'll use the distance between function we wrote to measure the first and second bones. Then, we'll add them together, creating a new variable with the total length. After this, we can point constrain the start locator to the base control, that's our shoulder, and the end locator to the local control at the wrist. Make sure maintain offset is set to false, so the locators snap into position of the control. Next, we'll connect our world matrix attribute into the distance between nodes in matrix 1 and 2 attributes. Now let's calculate the length ratio by connecting our distance into the input 1x of our stretch multiply divide node. We'll divide that by setting the input 2x to the total length. And to divide, we need to set the operation to 2. We also want to connect our limb distance into the first term of our condition, and the stretch MDN's output x into the color if true r. The second condition should be equal to the length total variable, and we'll want to set the operation to 3 for greater than or equal to. Next, let's add some attributes to the world control. For all intents and purposes, the attribute type double is a float value. I had to Google what the difference is. In Maya, floating point numbers are 32-bit. Double floating point numbers are 64-bit, so doubles can hold larger and more precise numbers. However, float values in Python are 64-bit. If you're ever unsure about something, just Google it. If I had $1 for every time I was asked a question that somebody could have sooner asked Google and found the answer, I would be able to retire. If I had $1 for every time I Googled a question I didn't know the answer to, I'd be richer than Larry Page. If you don't know who that is, well, you can Google him. When Googling a question about scripting, I first check out any results on StackOverflow.com, and that usually will answer my question in detail. I digress. Here we have the attributes to turn on and off our stretch, and the attributes to add or subtract length to the desired bone. Next, let's create the blend2adder node that we can use to turn on and off our stretch functionality. Set its first input value to 1, then connect the conditions outColor into the BTA's second input. Then we can connect the world controls stretch attribute into the BTA's attribute blender. Now let's create the plus-minus average nodes for each bone. Connect the up and low limb attributes into the first input 1D attribute on the PMA. Then connect the BTA's attribute into the second input 1D attribute. And last, set the input 1D's third attribute to -1. The last stretch connection will be coming from the PMA's output 1D into the respective IK joint's primary scale axis. There's a lot of information from this function that we'll want to use later on. What we can do is store this information in a dictionary. We'll want to store the measure locators, the length, the multiply divide node, and the condition node. We'll be calling back to these when organizing our rig and compensating for global scale. When we create a variable using this function, the variable's value will be equal to this dictionary. Now I'll just go back up to the top of this function and copy it. We've given our arguments the same name as our variable in the lim function. Because of that, I can just copy and paste this at the end of our lim function. Remember to put it in a variable. I've also added a condition, so if we wanted, we could build without stretch. For now, we want it on, so let's go up to the top and make sure add stretch is set to true. Before we move on to the FK stretch, I'm just going to do a quick test in Maya to make sure this is working with no errors. So if I run this and play around with my IK handle and the settings, you should expect to see everything behaving properly. Unfortunately, it is. Now we can start scripting the FK stretch. Let's create a function called addFKStretch. For this, we'll just need to pass in our FK control list, the FK chain list, and our primary axis. Let's start out this function by looping through all the controls. We'll want to count our iterations, so let's enumerate the FK control list. We'll add a condition to do this on every control but the last one. First, add the stretch attribute with a min value of 001. It's probably a good idea to set the min values on our IK stretch as well. So I'll go ahead and add that before I forget. Then we'll create a mult double linear node and an offset locator for the child joint of the current iteration. Next, parent that locator to the current joint and then move it to the child joint using A to B. We can define the offset value by using the locator's primary axis translation. We'll use that for our MDL's input 1 and connect the stretch attribute into the second input. Then we'll take the output of the MDL and put it into the locator's primary translate axis. We'll also connect the stretch attribute into the joint's primary scale axis. Let's check to see if the child joint has the offset parent matrix attribute. If it does, we can connect the locator's matrix directly into there. If it doesn't, then we'll create a decomposed matrix node and connect the locator's matrix into the decomposed matrix's input matrix attribute. This node basically converts our matrix into transforms. We can then loop through the translate, rotate, and scale and connect the DCM's output translate, rotate, scale into the offset group's transforms. Before we test this in Maya, let's go ahead and paste our addFKStretch function into the ifAddStretch condition. Now, if I play around with these controls and dial in some stretch, I can see that both our stretch functions are now successfully working. In the next lesson, we'll finalize our script by cleaning up our hierarchy, coloring our controls, and making a few additional connections to incorporate global scale. Thanks for watching, and I'll see you in the last lesson for scripting our lim. Hey there, welcome to the final lesson of Chapter 9. In this one, we're just going to be cleaning up our scripted rig a little bit. Step 1, let's organize our hierarchy. I'll go ahead and create a variable for all the groups I want to create. Then, using the group command, we'll create an empty group for each variable and name it accordingly. I know that I want to put my IK handle and the measure locators inside of the noExform group, so I'm going to scroll up a bit and make a list with just our IK handle. Then, if we go inside Add Stretch, we'll add the measure locators to that list. This way, we can add the list to the group instead of the variable names, which may not exist. Now let's parent everything into groups with the parent command. It's relatively straightforward where everything goes. We'll put the IK controls in the IK control group, the FK controls in the FK control group. Our bind chain goes into the skeleton group. We'll take our noExform list and parent it into the noExform group. Everything else, except for the skeleton group, can go in the limrig group. Then the limrig group and the skeleton will go into the all group. Then we can use transfer pivots to copy the pivot position from our first joint over to all the other groups except the noExform and all group. Using cmds.hide, we can disable the visibility attribute on all the joints and noExform group. Now if we run this inside Maya, we can see all our nice grouping. Let's bind the skin to our bind joints, then select the root group and see if we can scale up our rig. I can already tell you it's not going to work. What happens is, our stretch is being activated because the distance between our locators is growing. We need to make some new connections to tell this not to happen. To do this, we first need to add a global scale attribute. Let's put this on the all group. Then we can loop through our X, Y, and Z scale attributes, and for each one, we'll hook in the global scale. Now, the global scale attribute drives our scales. If we're using stretch, then we'll want to create a double linear node for our global scale. We'll set the MDL's first input to the length total of our limb and connect the global scale into the second input. Then we'll take the output of this node and connect it into the stretch multiply divide node's input 2x and the second term of the stretch condition node. Now if we test out our script, then bind our joints, we'll be able to see if the global scale is working properly. It looks like it is, so we can carry on with our cleanup. Let's give our controls some nice pretty colors. To do this, I want to go through and tag all the controls with an attribute that will relate to a specific set of colors. Let's make a little function to help us add this attribute. I'll call this tag control, and we'll give it a control and a tag name. To add a string control, we have to use the data type argument and set that to string. Then we want to use setAttr on our new attribute with the tag name and set the type equal to string. Next, we'll go to each control that we created and use this function to tag it with an attribute related to what type of control it is. For all the attribute names, I'll want to use the base naming in case we have multiple ARM setups and want to differentiate between them. In all, we have 4 different colors: primary, secondary, pull vector, and FK. Now let's find and color all the controls we tagged. If we don't pass in a color dictionary, we'll use a default one that we create. I'll create 4 keys. These represent the 4 types of tags we just created. Then give each one of these an RGB color value. Now we can search for all our tags by looping through a list created by ls side plus wildcard dot control type. We can use split to get the control name. Split will create a list by separating a string using the character you pass into it. The control name will be the first item in the list because color tag is the control dot attribute. To find the control type, we can just do a getAttr on the control tag. We only want to apply the color if our base name is in the control type. That way we don't accidentally color another limb. Then, using setAttr, we can enable our color override attributes and set the override color RGB to the value stored in our color dictionary. When we run our script, the limb colors are now colorized. Also, if you look at the transform on the control, you can see the control type attribute we added. Next, let's go through our controls and lock and hide the attributes we don't want to be animated. We can make a function called lock and hide. If attribute list is none or false, the attribute list will be translate, rotate, scale, and visibility. If nodes is not a list, we'll convert it to one. If any t equals attr for or T in translate, rotate, scale, is basically saying if any translate, rotate, scale attribute is in our attribute list, then do something. If our attribute is one of these, then we'll want to loop through this attribute's x, y, and z values. Each time through the loop, we're locking and hiding one attribute at a time. If it's not one of these three attributes, then we won't loop through x, y, and z, and we'll just lock and hide the attribute that we're passing through the list. Using our new function, we can lock and hide the translate, scale, and visibility attributes on our FK control list. Next, we'll lock and hide the scale and visibility on our IK controls. Then, for our pull vector control, we'll lock and hide everything except the translate attributes. For the settings control, we won't pass in any arguments. This will lock and hide everything in the channel box except for our FK-IK attribute. We'll also want to create a reverse node. This will drive our visibility on the FK and IK controls. When our IK control set is on, we want our FK controls to be off, and vice versa. Then connect the settings controls FK-IK switch attribute into the first input X, on the reverse node. We'll also connect the FK-IK attribute directly into the visibility on the IK control group. Now take the output X of the reverse node and connect it into the FK control group's visibility. The last thing I want to add is a templated line from our pull vector control to our elbow. I'll make a function and call it addGuide. We'll feed it the start and end transform nodes for where we want to connect our line. Then we can query the world space positions of our start and end controls. Next, using our curve control function, let's draw a line between the start and end position. Now we'll make a cluster on the start and end CV of our curve. The cluster command returns the cluster, then the cluster handle. We only need to access the cluster handle, so I'm going to store the second item in our variable. Then point constrain these to the start and end transform nodes that we provide as arguments within this function. Let's clean it up a little by setting the template attribute on our guide. We also want to make sure inherits transform is set to false. We want to return our clusters in a list, then our guide curve. Now we can go back up to our lim function and create our pull vector guide using the addGuide function that we just wrote. We'll take the clusters it returns and parent them into our noXForm group, and the guide curve itself we can parent into our IK control group. The very last thing we'll do is add an option to remove our guides. Not the guide curve we just created, but the guides we used to build our little setup here. We can do this using the delete command. Let's also go up to the top and set this argument to true by default. Let's go ahead and test our changes. When we select our controls, we should see the channel box is now much cleaner than it was before. Also, when we switch our arm state, only the active control set is visible. And that's it. Congratulations, you've scripted your first rigging module and completed Chapter 9. In the next chapter, we'll design and create a graphical user interface and link it to our lim function. As always, thanks for watching, and I'll see you in the next one.